A secondary effect.
Right. So, now Mr. Pauli, he was an elegant man. I mean, he's the one who talked about this exclusion principle. By the way, I mean, it's only today that we have physics departments, chemistry departments. Chemistry departments have, I mean, I might become unpopular. Chemistry departments have inorganic, organic, physical, and you have this separation. But what were people like Pauli, Dirac, Niels Bohr, Heisenberg, Schrödinger? Could you call them physicists or chemists or what? Or Van Vleck or Pauling? So Pauli is a person who gave the exclusion principle. He also said, let me simplify all these things, and I don't like this Planck constant, the factor of half, and we introduce instead these are basically multiples of this, and so these are called Pauli's spin matrices. Now, this Sx has this commutation property, is I h bar z. You remember all these things because you simply have x, y, z, and you go cyclic, then, and similarly. And you also have sx squared equal to sy squared equal to sx squared equal to h bar squared over 4. So similarly here, you have sigma x squared equal to sigma y squared. This is all algebra, right? It's called SU2 group if you want to be fancy. You couldn't do this. And the commutation properties also says that sigma y x sigma y is equal to I 2i sigma z, etc., etc. And you have a further property called anti-commutation property, that sigma x sigma y plus sigma y sigma x equal to 0. These are all things that you can see in elementary books in quantum mechanics.
So just to interject, making sure that the students don't miss that Sx squared, Sy squared, I mean, implicitly there's the identity of the matrix at the end, and not a number, because that is something.
This is, as Professor Dirisha was pointing out, is very important. These are all operators. So these are also operators, but there are multiples of unit operators. And if you measure Sz squared, you get, or S squared, like for instance, S squared is the eigenvalue of that will be actually h bar squared times S plus 1. Okay, so as he pointed out, that the way I have seen it written as though it looks like a number, it's not an ordinary number, it's a multiple of unit operator. And what's the unit operator? Unit operator is 1, 0, 0, 1. So it's let me come here. So 1 is like this. And between these four, you can map all two-state problems. Right? It gives you a language to play with. So now I complete this discussion here, either in terms of a double oscillator or in terms of two atomic systems that are brought together. And now we have a language. The language is that the left state of the double oscillator is what I want to call the minus state, and that is a column vector. Why? Because if I operate sigma z on minus 1, I know that I should get a downspin, right? Which must be the same thing as this, or sigma z plus 1, I must get this. And this you can verify by having this matrix and operate on these columns, right? Please do this as an exercise in the evening, okay? Right. So now, so then what we wanted to say is that what we found out here from this picture, that if I now start writing down what is the effective Hamiltonian, we said that there's tunneling. If I prepare a wave packet here and I let it go, then the wave function would overlap because I have this combination of symmetric and antisymmetric wave functions. So this is non-zero, and just as this is non-zero. Okay? And this overlap is something that will appear in Professor Sharma's lecture in the afternoon. It's called the overlap matrix element as the electron hops from side to side. And then, well, so far I have said that these two levels are symmetric, but you can easily imagine by either applying, let's say in the niobium problem, a stress or concentration of other impurities, or if you have a spin problem, you apply a magnetic field, and if these states are not degenerate, then these energies may be in general different, call it epsilon plus with a minus sign, minus. So I can now construct an effective Hamiltonian for this effective two-state system. For this effective two atomic orbital overlap system, two LCAO systems, right? So this effective Hamiltonian then is actually equal to, so this H effective is equal to, I'll tell you why I'm writing this. Why did we write this? 1 plus sigma z is what? You come here and you add, you get 2 here and 0 here. There's a factor of half. So that 2 becomes 1. So this is a projection. This projects the system into the plus state, because that fires, that matrix element fires only when I have the state to be plus. I should have said that whenever you label a matrix, you say what the basis states are. So I'm using this basis states, plus and minus. So this is 1 here. On the other hand, 1 minus sigma z is that you will kill this and you'll have 1 value here. So they are basically, this is actually a projection operator. I could have also written it as something that you might be familiar with. It is called a projection operator. The system is projected into the state plus by this operator. And then this is minus half, and I'm already now in time binding almost, and minus j sigma x. And what is sigma x? Sigma x is a combination of plus minus and minus plus. Okay? So this is your effective Hamiltonian for this two-state system, either for the double oscillator or when I do the LCAO for two atomic systems. Okay? So now, I take a pause. Plus and minus are two of your physical states. Think of them as two lattice sides. They are not the eigenstates of the Hamiltonian. The eigenstates of the Hamiltonian are the wave functions that I drew earlier. Okay? Because they are not eigenfunctions, I must have off-diagonal matrix elements of the Hamiltonian between these states, between plus and minus, and that's reflected in this term. Okay, and that's the tunneling term. And these are what are called the side energies. Okay? So, clear? Let me actually have 2 minutes according to Cheyne's clock, and so I simply write down the type binding model now, and I'll quit and take questions. So from this, now, from a two-state system, you graduate to a multi-state system. So HTB sorry, this is inside. Plus Hermitian adjoint. Okay? So these are what are called site energies, and these are what are called upping, tunneling, overlap, various names are given. And that's your simplest tight binding Hamiltonian. So the tight binding Hamiltonian is motivated by this bottom-up approach of nanoscience today, because in nanoscience, you actually now can have in the laboratory a single atom, a single molecule, two atoms, a qubit, like two fullerene, okay? And from that you can build up the ladder and go in the direction from Saurabh Pal to D.D. Sharma and Dattagupta, okay? So this is the tight binding. D.D. will talk even more complicated stuff of another energy parameter that will come in, and you have to be. So what Professor D.D. Sharma will tell you, how spectroscopically to extract these parameters, because I have only talked about in terms of parameters, in terms of overlap. What is the meaning of this delta or the J? What is the meaning of these epsilons? And electron spectroscopy will allow you to extract these parameters, and this is what Professor Sharma will talk about tomorrow. Actually, now that you mentioned this, yeah, I'll say something about that later on. That's something. In fact, relates to, you mentioned something which relates to Professor Sharma's lecture. When you do photoelectron spectroscopy, sometimes you do what is called the dipole approximation. That, you are essentially shining light on an atomic system or a molecular system or on a lattice, like the old photoelectric effect. You shone light on a piece of metal and extracted an electron, ejected an electron. This is what is done in the spectroscopy, which we will discuss more. And then you do what is, so you're now, from a basic point of view, you're interested in the interaction of a multi-electron system with the electromagnetic field of the incident radiation. Now, electromagnetic field has the vector potential, is got the electric and the magnetic field, etc. But you can do what is called a dipole approximation. It makes a lot of physical sense, because if the wavelength of the incoming electron, photon beam, is much larger than the atomic dimension, which normally is, like X-ray photoelectron spectroscopy. Atomic dimension is of the order of the Bohr radius or something. Then you will find that approximation, dipole approximation, where everything, then matrix elements turn out to be just those of the electric dipole matrix elements. Then the approximations are very good when Z is actually small. So another place where Z, I took the cue from your question that small z, large z come in, that the dipole approximation will break down when you go to large z.